Okay, so on the board right now we have the product of two complex numbers in Cartesian form. But let's now rewrite each number in polar form. And in polar form, the first number, let's say the absolute value here is R1, and the corresponding angle is alpha 1. And the absolute value of this one is R2, and the corresponding angle is alpha 2. Then this number can be written as R1 times R2, or using the notation that we just introduced, this is f of alpha 1 and this is f of alpha 2. That's sort of more compact, but I think it's good to see that intermediate step, and I'll group things like this: R1, R2, f of alpha 1 times f of alpha 2. And for this product, we've already established a formula that's f of alpha 1 plus alpha 2. That's the breakthrough. And this you can put in words. Actually, when it comes to defining the product of complex numbers in Cartesian form, you can't really put it in words. You have to say AC minus BD plus IAD plus BC. That's not really putting it in words. That's opposite. That's just reading the equation, which is not helpful. But when it comes to the polar form, the product can be defined, or at the very least described, as the product of the absolute values. So the result has its own absolute value, and I may not have mentioned this term, but the angle is called the argument. So the absolute values multiply and the arguments add. So to multiply two complex numbers, you multiply their absolute values and you add their arguments. And that's really putting it in words. I don't think I need to write it out as cosine of alpha 1 plus alpha 2 plus I sine of alpha 1 plus alpha 2. So I'll just leave it like this. Okay? And the most, I don't want to say the most wonderful thing, but when it comes to squaring, you just have to square the absolute value and double the angle. So let's write that. And not only that, not only can we square it, but just as easily we can raise it to the nth power. And notice that I'm kind of staying away from the geometric interpretation, which would have allowed me to draw a wonderful drawing of how the angles add up. And I guess I'll have to do that at some point. But at this point, it's really not necessary. It is the algebra that's just as clear. This kind of algebra is just as clear without a drawing as it would be with the drawing. So I think it's helpful to see that algebra holds up on its own without the geometric interpretation. So when we raise this to the nth power, we have okay, and this is now so simple. Think of how complicated this would have looked in Cartesian form. You basically have to use the binomial formula, and just about half of those terms will go into the real part of this, and half of those terms will go into the imaginary part of this, and it'll just be a mess. And there's no insight on how to invert it. Even though, as we're about to find out, that inversion is always possible. It's kind of magical.